Well, here we are again. Welcome to the physics video lecture. psci, actually, physical science. psci 168, video lecture 5. I'll begin with some announcements. First, concerning the email homework. So it worked out pretty well last time. I'm just going to reiterate for everybody. So this class will be sending me one email per week. And it's your name. So your name, psci 168, notes in the subject line. And everything should go in there. So if you take notes, you want to take some really beautiful notes. Pictures that you downloaded and printed out, you want to show me that you did those. Tables of values. Well, for example, the alphabet last time, we got the alphabet, that was nice. So you want to make that really thorough. I'm not asking for a second email, so if we have certain homework assignments that in the body of the lecture, I'll say do this or that for homework. Just work those and build them into this whole thing. Other physics classes, I'm having a separate email, but here we're just going to do one email with everything, and once a week, Friday, 6 p.m. Friday, 6 p.m. So that's the first thing. The other thing about the video lectures I wanted to announce, I will, starting next week, only have one in the playlist at a time. So this is video lecture 5, it's for a Friday. The next one, video lecture 6, will be on a Monday, and I'll hide the other 5. And then it'll be up until video lecture 7 is posted, and then 6 will come down. So that there'll always be one up at a time for at least a full day, possibly a second day. But then when I post the next one, I'll take that one down. So you want to make sure you get notes for all 3 of them, and then you turn, at the end of the week, you turn in the notes for all 3. Okay, I saw some good notes, so that's something that can really grow. Good, so that's what I was going to say about that. And today, we're moving on in our topics. I'm going to review the math a bit. And then we're going to be talking about force and structures. So you learn about force, basic abstract concept, but then we have a lot of concrete examples, and then we can discuss structures, which are a really good example of forces. And it turns out we need our triangles in our math as well. So that's how we're going to move along. Good, so in terms of the math that we've done so far, in terms of arithmetic, we just needed scientific notation. That will continue to be important. Scientific notation, laws of exponents, counting system. But in the geometry, we had a number of interesting things. In particular, triangles and similar triangles. Similar triangles. So our main application with the similar triangle, well, we did the height of a tree one. That's always a good skill to have. H, L, and then we had a lowercase h and a lowercase l. Both of these are right triangles. They're similar triangles, so we had h divided by l divided by lowercase l. And other relations among triangles. This one's going to play a big role. Okay, just these types of ratios. The other place we used it was in our shape and size of Earth graph. So remember that problem just reduced into this geometrical construction here. And we had these two angles that could be identified. We said that these lines were parallel. We had an arc length and a radius, and we had S is to 2 pi radius as theta is to 360 degrees. If you're measuring angles in degrees, okay? So those were two important geometrical applications of geometrical facts. What's going to come into play later on, we're going to take circles, triangles, and incorporate a Pythagorean theorem in a circle as well. So those are the things we're going to be using, and I'll be using these types of relations today when we talk about forces. So let's just call this our math review, our math reminder, as it were. And of course, there are other things up there as well that we did. So now I want to describe and discuss what forces are. That's a necessary step in order to talk about energy. You have to talk about force first. Oops, good catch. And talking about force allows us to talk about interesting things like structures, architectural structures. Good, so here we go. What is a force? Well, we all know some forces. Our weight is a force. You stand on the bathroom scale, you're measuring a force. Now, to start the discussion off, force is a push or pull. So if you push on something, you're exerting a force. If you pull on something, you're exerting a force. So I brought some objects here. Here's the bathroom scale I was talking about. Now, if I squeeze it, you see the dial there move a bit because I'm exerting a force on it. And I have another type of scale where we can pull on it, okay? Just to illustrate the pull a little better, I'll put a colored string here so you really see the idea. So when you pull on something, there's a tension force, and I move the dial as well. Okay, so you can pull or push on something, and that's a force. I haven't measured the name of the scale yet. We'll get to that. So the force is a push or pull. Example. Muscle sensation. So you have a sensation in your muscles when you do this, when you push or pull on something. So that's what a force is, just very generally. And now in terms of the next example, weight is a force. And we weigh things in pounds, usually. But here in this class, it's a physics class, we're going to weigh things at a different scale. It's called the Newton scale. So I have this object here. It has kg, kilograms on it, but I'm going to take an identical one that says newtons on it. And this bathroom scale actually has newtons as well, but now I'm going to demonstrate this thing here. Put this weight on it, it says 10 newtons. And the dish drops a little and this thing is pointing at the 10. Okay. So the unit of force is the Newton. Weight is a force. So next, the unit of force is the Newton. And what we do when we're talking about quantity quantities like this, we give them a letter. So for example, we can say the letter for force is F. And if I put a square bracket around the letter, I'm saying I'm going to write out what is the unit of that force, a square bracket. So the unit of force is the Newton, N. And so Newton is abbreviated with N. And how much is that? Well, this is a chunk of metal, 10 newtons. But here's something, actually got to go around the corner. Here's something. This is a 1 liter bottle of water. 1 liter bottle of water. There's your 10 newtons. So a 1 liter of bottle is 1 liter bottle of water weighs approximately 10 newtons. Okay. Now I have this piece of metal that says kilogram on it. It's also going to give us approximately the same 10 newtons, yeah, okay. But the kilogram is actually not a measure of weight, it's a measure of mass. So there's a difference between weight and mass. Namely, if I take this mass or this mass to the moon and put them on the scale, they're not going to weigh the same as they do on Earth. Even though they're the same object, they have the same atoms in them, same everything. So the mass is actually the quantity of matter, and the weight is a force that exerts here. So on Earth, under gravity, the weight is what we're measuring when we drop something on a scale like this. Okay, I could actually take this balance, and see how close our water and our chunk of metal are. I doubt they're exact. Well, they're pretty darn close. Let's see. Pretty good, actually. Okay, you see they're actually very close. And if we were to take a tiny bit more water out, we'd get it to balance perfectly, and then we'd say, you know, it's the exact same. Mass, same weight. So mass will come into play a bit later in the semester. Right now, when we're talking about force, we're talking about the push or the pull and the weight. So once more, I'll underline weight. And we've got these examples. I'll put that right there for the moment. And I do want to get a conversion here. So you see I was pulling on the scale, I'm pushing on the scales. Push or pull, that's a force. It gets a reading on the scale in newtons. And I'll put here the conversion. You could say this is the exact conversion. We have 2.2 pounds equals 9.8 newtons. Okay, so you can always convert from one to the other. Okay, suppose you want to know how many newtons you weigh. Well, you could jump on this scale here, and it has a scale in newtons. I don't know if the N is visible there in the middle of the bathroom scale in newtons. Or you could use this conversion. So my weight, so I'll write it out again. Weight equals X. Do I need some number here? I'll use the N pounds, and now I want to convert. So I say I have 9.8 newtons divided by 2.2 pounds. Okay, that's a conversion, and then you'll get the answer. Okay, so this is my number of pounds, N, and this ratio here, you could say that is 1. That is equal to 1. Notice if I have this expression here and I divide both sides by pounds, my 2.2 pounds, I'm left with a 1, and that's what I multiplied this by. So that's how you convert, you know, n is a bad number for, use lowercase n, because we just gave uppercase n for newtons. Okay, so finally, this is the number equals number, multiplied by this, divide by 2.2, and then you'll get your weight in newtons, okay? Something you always wanted to know. Now you know how to get that. So we have force, it's a push or a pull, and a weight is an example of a force, a tension pulling on something, example of a force. So that should be good for there. So the next topic is called simple addition of forces. So how do forces add and subtract? So simple addition of forces. And we'll demonstrate. So we've got this scale here, and individually we have, I should probably look here and control it. We have 10, and we have another 10. So when we add them together, put them both in the good. 10 plus 10 is 20. Okay. And I'll give a couple of other examples of the same thing. Now I have two scales. Nice to have a helper for these kind of things, but we can pull this off. So I have two scales, and we'll first of all demonstrate. We've got the 10 Newton weight here. Close enough. Okay, so we've got 10 newtons. Now if I do two scales, okay, let's shorten this string a bit. Yeah, here we go. Okay, two scales, do it like this. Go. It's more of a feeling. Okay, trying to make a simple point. Hope this works. Just check. Good enough, yeah. See, now I am splitting the 10 newtons between two scales, and I'm getting 5 plus 5 roughly, okay? And if I put a little more on one side than the other, I can do things like 6 plus 4 and 7 plus 3. So when we talk about simple addition of forces, I'll just draw a couple of these demos. You know, on this scale here, I put in 10 and 10, and then this thing showed 20 newtons, okay. Or I took a 10 Newton object and I hooked it up to these two scales, and they read 5 and 5. And another demo that I would, if we were together in class and I had two bathroom scales, I could do this. I could, here we go, stick figure. So these are the two bathroom scales I'm standing on. And my weight equals, say, 800 newtons, except it's more. I'm sure it's probably about 900 newtons. Let's say it's 900 newtons. And then what would my reading here be? I could have 450 newtons, 450 newtons. But I could lean on one scale more than the other. So I could certainly have or 200 newtons and 700 newtons, okay? So I've made my point, right? This is called simple addition of forces, and the slogan here would be, forces add like numbers. Okay, so that's the slogan. I'll put scare quotes around it. Forces add like numbers. That's simple addition of forces. So now the question comes up, what if we start including some angles in the scenario? Okay, what I mean by that is the following. First, let me clear some of these distractions out of here. Okay, put them right back here. So these guys I don't need. These two I do need. This I also need. So here's the question. Suppose I take this self-same 10 Newton chunk of metal that we like to use here, 10 newtons, right, we saw it, and I suspend it from my string like this. You already saw me take two scales, so what if I do the two scales like this? What is the reading going to be? Okay. We just saw simple addition. Are we going to get, if I keep it completely symmetrical, are we going to get 5 newtons plus 5 newtons equals 10 newtons? Okay. That's the question. And I'll answer it quickly. You know, with a big class, I can take a show of hands and ask who thinks what and so forth, and then we can demonstrate this together. But I'm just going to have to do it on my own here. We're taking a 10 Newton weight. We've got these two fine scales. Okay. We're going to start with the 5 plus 5. Yeah, it's around 5 plus 5, 6 plus 4. Okay. Now I'm just going to, pardon me, here we go. Okay, now I'm just going to start pulling this out, and I don't even have to see it to know that we're no longer reading 5 plus 5. What are we reading here? I can, at this point, I'm probably going beyond the 20. Okay. Oh, break it, huh? Okay. So anyway, just hold on to that. It's definitely more than 5. I'm guessing it's probably around 20. So what's going on here? Triangles, okay. This is something that needs an explanation. So this is where forces become interesting. Okay, the question is clear. Put in your notes what the question was. What are these scales going to read? I just did the demonstration, and we did not have 10 equals 5 plus 5. We had 10 equals 20 plus 20 or something, depending upon how hard I was pulling outward. So what we're looking here is called vector addition of forces. Vector addition of forces. Well, vector is a technical term for something in mathematics that we're about to learn. Vector addition of forces, the slogan that goes with this is forces add like vectors. Oh well, that doesn't tell us anything. Forces add like arrows. Forces add like arrows. And how do arrows add? They add in the way that any child could add arrows. We would just put them up against each other and see where they end up. Okay. So an arrow, for example, this arrow plus this second arrow, got a horizontal and vertical arrow, equals, now I'll do this one in red. The sum of these two arrows is this diagonal arrow. And you'll notice it's a well-defined triangle. The sides are well-defined. If I did a good job, I actually kept these lengths exact. And that's how forces add. Forces add like arrows. Now I'm going to do my explanation right here on this drawing, okay? You could draw another one actually, because then this was the question and the next one would be the answer. Forces add like arrows. So what happened here was this force, in other words, this blue line represents a force, and in fact it represents the force of whatever magnitude we read off on the scale. But because forces add like arrows, we can say we actually have a horizontal force plus a vertical force. And over here we have a horizontal force plus a vertical force. The horizontal forces are like the tug of war. We're pulling against each other. They're both exactly the same. Nobody's winning, okay? We're pulling against each other. But the two vertical forces are actually pulling against gravity. Okay? So it's these two verticals that are pulling against gravity, and we can even attach these lengths here once, twice. We could say we have a vector that's 5 and 5. So these two add like numbers, right? Like simple addition of vectors, 5 plus 5. So this would be 5 newtons. This would be 5 newtons. But, and by the way, this picture, this is the explanation. So make this one really accurate, as accurate and clear as you can. So these two 5 newtons are what's lifting the 10 Newton weight. But the actual force that the scale is measuring is this string. So we just measure off the length of these. I'm getting 5, 10, 15. So I'm getting about 18 or 19 at these particular angles, okay? So I'll just say, in this particular example, it looks like about 19 newtons. But you'll notice it's truly the proportionality that's inherent in this particular triangle, okay? So knowing triangles, knowing that geometry, we immediately can understand vectors. We don't have to do anything fancy. So forces add like arrows, and actually, technically speaking, we say forces add like vectors, but vectors add like arrows, as I showed right here. Okay, so yeah, this is the really crucial and important example. And you know what I'm going to do? I think I have some stronger scales backstage here. So bear with me. Okay, so I'm back with a couple scales that read 50 newtons. Okay, these are 50 and 50, and we're going to do the same thing we did here with the other ones. Let's see if we're still running this show. Okay. Okay, we have 2 scales, each 50 newtons. 50 newtons. And you can see when I put 10 newtons here, it just goes to the 10. And we're going to do the same thing we did a moment ago. And you know, if you can see this on your screen, you could conceivably check the accuracy of this. Okay. Speaking of screens, I don't know if I had mentioned this before. If you watch these videos on a full screen, so you take YouTube, go to full screen, I've been able to read anything and everything I've written there. So first of all, on full screen, and second, on high resolution. So the highest resolution setting that YouTube offers, you know, you find the settings and open that up and get the high resolution if you haven't been getting it before. The quality goes up markedly. Okay, so here we go. So we'll start with the, you know, the simple edition, but we're now going to go out here and make this very flat. I don't want to break the thing, but yeah, see, I can have 50 and 50. Okay, 50 on one side, 50 on the other. And you'll see how flat this triangle is. So this would be like a 45-degree angle. This is very flat. And I've got a lot of force there. Okay. So I showed you that just in order to do a second construction, because this vector question is so important. And we'll get some great applications of this in what follows. So I'm going to make another sketch here. Actually, let's check again. Okay, good. We've got plenty of time. So same example. Now we know what's going on. And I draw my scale example, you know, very flat. There's the hook. There's the other scale. Okay, it's very flat. Here's our 10 Newton weight. What's the tension going to be? I should have made these symmetric. They're fairly symmetric. Okay, we're just going to work on the right side here. So what is the tension? The tension is shown to be just by geometry. So what I do is I do a horizontal line and a vertical. Okay, horizontal and a vertical. And now, you know, I can do the same thing on both sides. This vertical represents 5 newtons. So here I would have 5 plus 5 equals 10 newtons in the simple addition. But since this represents 5 newtons, I'm just going to measure off. Okay, so I've got this little distance. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. Well, let's do this again. Well, I'm just doing it with my fingers, but let's say it was 12, okay? If that's 12 times this little length here, then since I have 12 of these, 40, 50, 55, 60, then I have 60 newtons equals 12 times 5 newtons. And this is a right triangle. So triangles, right triangles, similar triangles are necessary to understand forces. By the way, the flatter it is, the greater this tension. If you try to make it perfectly flat, you're going to have an infinite tension. So before you get it perfectly flat, you'll actually break your string. Good, but this is the vector nature of forces, vector addition of forces. So forces add like vectors. I'm not going to write it down again. You've got it there. These two boards show you everything. Okay, so what is that good for? So this next topic is called forces and structures. And we can understand things now that we see and that we've seen every day. Nature of forces and structures. And this also takes us through the history of architecture, and you'll be able to find many excellent pictures to illustrate your book with when we look these things up. So let's just call this forces and structures. And I'll just show you a quick definition of these things and their name, and you can get pictures of any of these, any and all of these for your book, for your notes. The first one is when you have, well, here's the ground, you have a couple of uprights, and then you just put something across the top. And that's called post and lintel. Post and lintel. So that's a really early type of structure. And you'll see it's making use of simple addition of forces, because if this cross beam here weighs 10 newtons, then if you support it symmetrically, or let's say 1,000 newtons, then you would have 500 and 500 on each side. So that's simple addition of forces. And you could, in fact, if you were going to draw it here, you could have its weight, and then what's holding it up would be half of this on each side. So you'd have half of that length, half of that length, because these two arrows have to have the same length when you add them together as that one, okay? That's the post and lintel. So Stonehenge, for instance. In fact, I'm going to show an interesting video that involves Stonehenge, or I'll put it in your list later. Stonehenge, that's in England. But you'll see other post and lintel as well. Okay, what do we have next? Next we have the arch. Okay, and I'll start with the Roman arch, which is based on the half circle. So if you have a semicircle here, say you want to do this, okay, and you just have stones, then you actually have to cut stones, and in particular up here at the top you need what's called the keystone. So here this is called keystone, and you see this shape of the wedge. This shape of the wedge, and what we now know about forces, ensures that when this thing presses down, these wedges press out, these sloping sides press out, and so there's an outward pressure, and you want that outward pressure to go all the way down the ground like that. There is a danger, that the whole thing will buckle, okay? And to get around that danger, they have to be made very thick, the arches. But the keystone is important to understand. So you've got your Roman arch. And what the Romans did with the Roman arches, they put a bunch of them together and they would make bridges and stuff. So there's the basic picture. Let's draw a couple of these. Like this. And then you put a roadway across the top. And maybe you have a river flowing through there, and you've got an embankment, okay? And that could be a road, a bridge, an aqueduct. And yeah, down here, you've got water flowing. How does that look? It'll do, okay? So yeah, you can get, there are famous Roman arches, by the way. There are famous bridges, famous aqueducts. So look some of these up and get some images as well. So let me just write here, just for the record, homework, images of all of these. And you'll find really interesting stuff on your search for post and lintel, Roman arch, aqueducts, just the arch, the keystone, very important concept, and so forth. See how we're doing time-wise here. I've got a lot of structures I want us to at least review. Okay. Let's do a couple more. I see we're not going to get through this completely, that's all right. 3, we have the Gothic Arch. So the Gothic Arch is kind of, it's a pointed arch. Okay, and I'll just write here, cathedrals. But actually what I should start with, and I'm going to put this forth, is your basic roof gable. So, you know, I've got this little progression historical. There's one thing missing, and that is the following. Suppose we have walls. And if it's too far apart, the post and lintel system is going to be difficult, maybe because that top beam is going to buckle, and instead we cover the roof like this. Okay. Now this is an interesting problem from the following standpoint. Suppose I'm standing on this roof with one leg on each side. Where is my weight going? Okay, this is the exact inversion of our strings. Okay, so I'm my usual 900 newtons. So I've got 450 here and 450 there, but I've got the outward one as well, because the actual compression here is along the blue line, along the roof. Okay. What happens is now these outward forces are going to push these walls apart and down unless I do something. Okay. So this is the example that ties all these things together. There's going to be an outward force, and you're going to have to do something. You can string a cable across to hold things together. If you don't want to string a cable across, and you know this outward force is going to be there, then you may have to build substructures, either make the wall thicker or buttress it somehow to capture that force and keep it from tipping those things outward. So yeah, these outward forces are the most important thing here. When we invert our force triangle with the string, we're still getting those outward forces. So here's 900 newtons, here's 450, 450. And if I measure these off roughly 1, 2, 3, 4 times or so, then I've got 1,800 newtons pressing outward. Okay. So the outward force is so important. And the Roman arch has a tendency to buckle. If you do several arches, you capture the outward force and eventually you send it to the riverbank. Okay. Gothic cathedrals, they have an outward force, okay, which is going to tip these walls, and they literally do what's called build flying buttresses. Okay. So for the Gothic cathedral, we have the expression of the flying buttress. Okay. Yeah, we're about to wrap this up on this one. So far, you've got your roof gable, your post and lintel. Actually, the logical sequence here, because I skipped this gable for some reason, you would actually go from the post and lintel to this roof gable. The roof gable gives you the whole problem. Outward force is about to tip these walls, and then these various arches are the solution. These flying buttresses are the solution. So you get some pictures as nice as you can of all of these examples. You know, if you can organize more than one picture on one page, print it out, knock yourself out. The more beautiful it is, the more you're going to enjoy your book. But what you have now is the knowledge of how all of these structures are dealing with forces and their vector nature. By the way, the Gothic cathedrals, maybe if you plug into the search engine Gothic cathedrals and forces or and vectors, because I know engineers have analyzed these skeletal structures, they're beautiful. Once you understand the vector nature of force, you're going to see things completely different. So good, I'm going to end right now with the Gothic Arch. We have a few more structures to deal with, because I also want to talk about the Pantheon in Rome. I want to talk about bridges, and bridges are also going to show the vector nature really well. Okay, so far so good. This will be the end of lecture 5, and we'll see you next week at lecture 6.